Greetings. This is the third lecture on the Riesz representation theorem. As on the previous lecture, we will work in a topological, locally compact Hausdorff space, X tau. We already introduced the Riesz representation theorem once before, but now we can be more specific about the hypothesis, so we will introduce it again. Assume that F is a sigma algebra on X which contains the Borel sets, but may be larger, and let mu be a measure defined on F. Such measures will be called Borel measures. Assume, in addition, that mu assigns a finite value to every compact subset K of X. Under these assumptions, the space CC of X of compactly supported, complex-valued, continuous functions on X is a subspace of L1 mu. It follows that the mu integral of F can be used to define a complex-valued linear map, that is, a linear functional, on the space CC of X. Let's denote this map by lambda mu. The map lambda mu has the additional property of being positive. If the function f only takes non-negative values, then lambda mu of f is also a non-negative real number. It is worth emphasizing that the positivity of lambda mu does not mean that lambda mu only takes non-negative values. In fact, since lambda mu of f and lambda mu of minus f have opposite signs, it is not possible that the range of lambda mu is contained in the non-negative reals, unless mu is the zero measure. Now we are prepared to state the Riesz representation theorem. It is the perfect converse to the previous observation. Every positive linear functional on CC of X is induced by a Borel measure. The precise statement is theorem 2.13. Let X tau be a locally compact Hausdorff space, and assume that lambda is a positive linear functional on the space CC of X. Then there exists a sigma algebra F which contains the Borel sets, and a unique measure mu defined on F such that the following properties hold. The measure space XF mu is complete, and the functional lambda is represented by the measure in the sense that lambda f equals the mu integral of f over x for every function f in CC of x. The measure mu also satisfies the following three regularity properties A, B, and C. Property A states that mu assigns a finite value to all compact sets. Of course, this requirement is already necessary to make sense of the integral above. Property B states that if E is any set in the sigma algebra F, then the mu measure of E can be expressed as the infimum of all mu measures of open sets U which contain E. Property C concerns a set E which may either be open or alternatively any set in the sigma algebra F whose mu measure is finite. Under one of these two hypotheses, the mu measure of E can be written as the supremum of the mu measures of compact sets K contained in E. Thus, the properties B and C tell us that the mu measure of a fairly arbitrary set E can be approximated from above and below by the mu measures of more regular sets. The approximation from above happens via open sets, and the approximation from below happens via compact sets. The condition C is a tiny bit less satisfactory than B, since we can't guarantee approximation from inside for all sets E in the sigma algebra F. We either have to assume additionally that E has finite mu measure, or then restrict attention to open sets. Under our current hypothesis of the Riesz representation theorem, this caveat is unavoidable. However, in later sections we will discuss how to remove it in some better behaved spaces, such as Euclidean spaces. We mentioned that the Borel measure satisfying the exterior approximation property B for all Borel sets is called an autoregular measure. Similarly, a Borel measure satisfying the interior approximation property C for all Borel sets is called an inner regular measure. A measure which is both outer and inner regular is of course called regular. The annoying caveat we just discussed above can be rephrased by saying that the measure mu in the Riesz representation theorem need not be inner regular. The property C is only guaranteed for Borel sets with finite mu measure, but not all Borel sets. If we additionally assumed that every open subset of X is sigma compact, then the caveat would vanish. This is in particular true if X is Rd. We will return to this point after the proof of the Riesz representation theorem is complete. Now we have spent some time digesting the statement of the theorem, and it is time to begin the proof. You are excused for missing this, but one of the statements in the theorem was the uniqueness of the measure mu. We will start by proving this claim, since the argument is much shorter than the existence part of the theorem. Let's start by reviewing precisely what we even mean by the uniqueness statement. Let F be the sigma algebra defined in theorem 2.13, and let mu1 and mu2 be two measures defined on this sigma algebra, both of which represent the positive functional lambda. In other words, lambda of f equals the mu_j integral of f for both measures mu_j, and for all functions f in Cc of x. Additionally, assume that both measures mu1 and mu2 satisfy the three regularity properties A to C listed in the theorem. Then the two measures assign the same value to every set A in the sigma algebra F, or in other words, they are the same measure. In particular, since F contains the Borel sets, the measures mu1 and mu2 agree on Borel sets. Before we start the proof, it is worth emphasizing that the equality of the two measures mu1 and mu2 takes more than the assumption that they both represent the functional lambda. We will really need the regularity properties A to C in this argument. So our uniqueness claim does not rule out the possibility that there might be additional, less regular measures which also represent the functional lambda. In yet another words, uniqueness only holds within the class of measures satisfying the properties A to C. Now we understand what we are supposed to prove, so let's prove it. The first step will be to prove that mu1 and mu2 agree on all compact sets K. We fix a compact set K, and we start by applying the outer regularity assumption B to one of the measures, let's say mu2 for example. Given any positive epsilon, there exists an open set U which contains K and whose mu2 measure is bounded from above by mu2 of K plus epsilon. Now we are in a situation where a compact set K is contained in an open set U, and we may apply Urysohn's lemma. There exists a continuous real-valued function f, which is compactly supported on U, only takes values between 0 and 1, and equals 1 on the set K. With the function f in hand, we make the following estimates. First, the mu1 measure of K is bounded from above by the mu1 integral of f, simply because f dominates the characteristic function of K. Second, since mu1 and mu2 both represent the functional lambda, the mu1 integral of f equals the mu2 integral of f. Indeed, both of these values are equal to lambda of f. Next, since f only takes values between 0 and 1, and is compactly supported on U, the mu2 integral of f is bounded from above by the mu2 measure of U. Finally, the set U was chosen so that its mu2 measure is no larger than the mu2 measure of K plus epsilon. Letting epsilon tend to 0 finally shows that mu1 of K is no larger than mu2 of K. By symmetry, the opposite inequality also holds, and hence we have shown that mu1 and mu2 agree on all compact sets. It is interesting to note that the outer regularity of mu1 and mu2 was already used in this argument, but the inner regularity will only come up next. Namely, next we claim that mu1 and mu2 also agree on all open sets. This is clear from the property C. If U is any open subset of X, then the mu1 measure of U equals the supremum of the mu1 measures of compact sets K contained in U. But we have just showed before that this supremum is the same for mu1 and mu2. Hence, by applying the inner regularity once more, we see that mu1 and mu2 agree on open sets. Finally, if A is an arbitrary set in the sigma algebra F, then we may use the outer regularity assumption B to conclude that since mu1 and mu2 agree on open sets, they must assign the same value also to A. This concludes the proof of the uniqueness claim. It is worth noting that the inner regularity for all sets in the sigma algebra F was not necessary in this argument. We only needed it for open sets. Another similar remark is that the completeness of the measure spaces X, F, mu j was never used in the uniqueness argument. On the next lecture, we will turn to the more essential part of the Riesz representation theorem, the existence of the sigma algebra F and the measure mu. Goodbye for now.